Hi everyone, my name is Pradyumn Kejriwal and today we'll discuss the solution to the 29th problem from the CP sheet by TLE Eliminators under the rating of 1400. So let's begin. So I have my sheet here and I'll open this problem called Queen. It says that you are given a rooted tree with vertices numbered from 1 to n. A tree is a connected graph without cycles. A rooted tree has a special vertex named root. Ancestors of the vertex I are all vertices on the path from the root to the vertex I except the vertex I itself. The parent of the vertex I is the nearest to the vertex I ancestor of I. Each vertex is a child of its parent. In the given tree, the parent of the vertex I is the vertex Pi. For the root, the value of Pi is -1. So it's just basic tree stuff. You notice that some vertices do not respect others. In particular, if Ci is equal to 1, then the vertex I does not respect its ancestors, and if Ci equal to 0, it respects all of them. You decided to delete vertices from the tree one by one. On each step, you select such a non-root vertex such that it does not respect its parent and none of its children respects it. If there are several such vertices, you select the one with the smallest number. When you delete this vertex V, all children of V become connected to the parent of V. Okay. Once there are no vertices matching the criteria for deletion, you stop the process. Print the order in which you will delete the vertices. Note that this order is unique. Okay. So the problem is pretty this statement was somewhat complicated. I'll just simplify it. Okay. So what they are saying is we have been given a tree, right? Let's draw it in white. So a tree we have been given, and it is rooted, right? So this is the root, and like these are children of these. So this vertex is the parent of this vertex, and so on, right? So let's say we have this tree. Okay, let's say we have this tree. All right. Now they are saying that on some nodes 1 is written, and on some nodes 0 is written. So let's say something like this is there. Okay. So on some nodes 1 is written and on some nodes 0 is written, right? And then what they're saying is, let us just number these nodes like 1, 2, 3, 4, 5, 6. Okay. So there are some numbers written. I mean on the nodes, the nodes are numbered from 1 to n, right? And on the nodes either 0 is written or 1 is written, right? So what they're saying is we have to delete the nodes one by one. Okay. And we can delete a node if and only if. So there are two conditions. Like we can delete a node V if and only if, first thing, the color of V, I mean the number written on V, has to be 1. Okay. And also the color of all children of V has to be also 1. So like we can delete a node V if and only if its color is 1 and also all of its children are having color 1. Okay. So here for example we have the node 2 and we cannot delete it because its child is not color 1, right? Then we have this one node. Okay, and we also cannot delete the root. Like deleting the root is not possible. Alright. So yeah, this is the thing. Then let's say we have this node. So this is 1 and all of its children are also like not 0. Basically it doesn't have any children, so you can delete this, right? Then this 7 node also is there, so you can delete this because it is itself 1 and its children are also 1, right? You can delete this 9 node also because its children are also 1 and it itself is also 1, right? So what you will do in this case is you will delete this 6 node because it is the smallest numbered. Like if there are multiple deletable nodes, like these 3 vertices, they are deletable, right? As I told you. So if there are multiple, then you will delete the smallest number, right? So out of 6, 7 and 9, smallest one is 6. So you delete that. So you have to print that in what order have you deleted those vertices. Okay. So yeah, this is the problem. And the constraints are that the constraints are that n is up to 10 to the power 5. So like the number of vertices in the tree is up to 10 to the power 5. So of course you cannot do O of n square solutions, because 10 to the power 5 ka square would go up to 10 to the power 10, which would give TLE, right? And so yeah, you can do it in like O of n or O of n log n, O of n log n, or something like that, right? So just pause the video and try the problem by yourself. You can see the sample test cases if you want. Like they are pretty simple only. Okay, so you can pause the video now. Alright, so I'm assuming that you have tried the problem by yourself and you want solution. So let's try some examples to understand what's going on. So I will use this example. Okay, so I just copy this image right here. Alright. Okay, so what's going on here? Let's see. Now first of all, I have to tell you the colors also. Like either it is 0 or it is 1. So which one it is? So I'll just mark the 0 ones, or I'll mark the ones which are 1. I'll mark the ones with yellow color. Okay, so let's say this is yellow, this is yellow, this is yellow, and also these two are yellow. Okay, so in this case we have to determine that what is the order, or let's say even this one is also yellow. Okay, so determine that what is the order of deletion. Okay, just ignore this thing because doesn't matter. So yeah, one thing I forgot to tell you, that when you delete a node, all of its children get connected to its parent. Like here the children of 7 are 1 and 6, right? So they will connect to its parent, which is 4, right? So that's what they are showing here. Okay, so yeah, in this case what we can delete, like if all of these are 1, then what we can delete? Now remember, we have to, like, we can delete only if the color of V is 1 and also the color of all children of V is also equal to 1, right? So can we delete this 2? No, we cannot, because this 5 is not 1. Then can we delete this 7? Yes, we can, because all of its children are yellow. Can we delete this 3? Yes, we can, because all of its children are non-1. So we can basically. We can delete this 1 also, 6 also, and 8 also. Alright. So here the answer would just be, like first we'll delete this 1. Right. So the tree would look like this. Right. So 1 is the answer. I mean 1 would get added to the answer. Then we will delete what? We cannot delete this 2. Still, we can delete this 3. So we'll delete that. And 3 is the answer. Then out of 6, 7 and 8 and 2, can we delete any of them? So 2 we cannot delete, and 7 we can delete, but 6 also we can delete. So we'll delete 6, right? Because it's the lowest number. So we'll delete 6 and 6 added to the answer. And when we delete 6, that means we are connecting this edge. Like this 8 gets connected to 7 directly, right? So this edge is added, right? Now we have 7 and we have 8. So can we still delete 7? Yes, we can delete 7 because its children, which is 8, it is 1. So we'll delete this 7. So we delete this, and the 8 gets connected to the 4 directly, right? So 8 gets connected to the 4. And can we delete this 8? Yes, we can. So we will just delete this 8. And this is your answer, right? So this entire thing that I told you was just the sample, one of the examples, just to understand the problem a bit more clearly. Okay. So one thing that I can claim in this problem, like I'll just directly move on to the solution. Okay. So first thing that I want to claim in this problem, so I'll write it. So first thing is that a vertex which is not deletable at the beginning, okay, will never be deletable. मतलब can never become deletable. Okay. So what I am saying is that let's say we have a vertex which is initially not deletable. Then I am saying that even after doing some operations, okay, so like when you delete some vertices, then it changes the edges, right? So I am saying that initially if it is not deletable, then even after changing the edges, it will not be deletable. Okay. And why am I saying that? Let's prove it. Okay. So the first thing is that let's say we have this node. And there's a lot of children of it, and it is not deletable. So if it is not deletable, that means what? Either it is 0 itself, then of course we cannot delete it, and in the future also we will not be able to delete it, because 0 we cannot delete. We can never delete 0, right? And like if it is 1, then definitely one of its children is 0. So like either this or this or this is 0. And because if any of this, like if every one of this was 1, then this would be deletable, right? So I am saying that if this vertex is not deletable, that means that at least one of its children is 0. At least one of its children is 0, right? So my point is that since this child is 0, you can never delete this child. Obviously, you can always delete only once, right? You can only delete once. So definitely you cannot delete this child which is 0. So definitely this 1 can never become deletable, because it will always have this child, right? It will always have this 0 child. So you cannot really delete it. So that's how we can prove that any vertex which is not deletable at the beginning can never become deletable after some operations also. Alright. So this is the first claim. And second claim is that a vertex which is deletable initially is always deletable. Okay. So what I am saying is, if there is a vertex, let's say again same example, let's say this is the vertex which has 1 and it is deletable, like basically all of its children are also 1. Okay. Then I am saying that whatever operations we do of deletion, like whatever I delete, this vertex will definitely always be deletable. So what I am saying is that this vertex will always have all children equal to 1 only, never 0. So what I am saying is, after any number of deletions, I can never make any child of this vertex 0. Okay, like whatever I do, it won't have a child of 0, right? So how will I prove this? So this is also quite easy to prove. Okay. So my claim is that a vertex which is initially deletable is always deletable. So why would I be wrong? Like why would this claim be wrong? This would be wrong when after deleting something, or like some descendant becomes my child and it is 0. That's what it can happen. Like that's what can happen. That initially this 0 was not my child. It was my child's child, let's say, like this. But then I deleted this and it became my child. And then, so I am not deletable anymore. So that's what can happen. Like that's how it can lose its deletability, right? But my claim is that can never happen, because let's say if you have like this, that you have this deletable node and then these ones, because it is deletable, so all of these are ones, and then this is a 0, and then you are saying that what if I delete this and it becomes its parent and now this is no longer deletable. But my point is that if this is 0, then you can never delete this vertex, right? Because to delete a vertex you have to have that all children should be 1. So you cannot delete this vertex, and therefore this 0 can never become the child of this 1, and therefore this 1 will always be deletable. Okay. Now you might be thinking, what if there is a 1? Like, let's say there is a 1 here, and there are 2 1s here, and there is a 0 at the end here. And finally, let's try to make this 0 as the child of this, so to disprove. So let's say we delete this. So this is deletable, this is fine. This edge is created. Now this is also deletable, so we can delete this, and these 2 edges are there, right? But the thing is that this is not deletable. We cannot delete this. So like, our aim of making this 0 as a child of this 1 has failed. So that's my entire point. We can never like, my point is that a vertex which is deletable initially will always be deletable, right? We can never make a 0 child of something which initially has all 1 children, right? So these are 2 claims which I am making, that a vertex which is initially not deletable can never become deletable, and a vertex which is initially deletable is always deletable. So whatever operations I am doing, they do not affect the deletability of my nodes, right? So like, in this case, as you can see, like, we had this example, right? So I'll again draw it. So let's say we had this we had these nodes as yellow, right? Okay, so I'll mark the deletable ones with red. Like, I'll mark all the nodes which are deletable with red. Okay, so 2 is not deletable initially because it has 5 as a child, which is 0. 7 is deletable because both of its child are yellow, so it is deletable. Then 3 is deletable, 1 is deletable, 6 is deletable, right? And it is also deletable. So I have these 5 deletable nodes initially, and according to my claims, these nodes will definitely always be deletable, and none of the other nodes can become deletable ever again. So what will I do? In my order, I will of course delete this 1 first because it is the lowest, right? And now after deleting this 1, only these will be deletable according to my claims. Then I'll delete this 3, then I delete this 6, then this 7, and then this 8. So essentially, you just have to figure out that which vertices are deletable initially, and then just print them in ascending order, because that set never changes. So one by one you will delete all of them, and since it is told to you that you have to delete them in the ascending order, like if you have multiple options at some point, you have to delete the minimum one. That's why you will just print all those vertices which are deletable initially in sorted order. Alright, and that's how you solve it. But one thing is that how do we determine that initially which vertices are deletable? For that, it is just easy. Like, you can simply iterate over all children. Like, if you have a tree, let's say you have this tree only. You had this tree with these yellow vertices, right? So what you will do is you will iterate over all the nodes, okay? And if it is itself deletable, like if the node is itself deletable and all of its children are also deletable, then you will say that it is deletable initially. So you can simply iterate over all of its children, like just iterate over all nodes, and for every node iterate over all its children, okay? And just check if all of them are yellow and it itself is also yellow, and if that is the case, then that node is deletable, okay? So that's the entire thing that you can do. So now let's look at the code. So in the code I have the fast IO, and like I don't need this CINT वैसे, but I just made it 1 and I'm calling solve function. So it is just template. Like if you have test cases, then just uncomment this and it will work, right? Then my solve function, I have int n cnn, like I'm just taking the input. So in the input format is like they have given the n node information. Like for every node they have given the parent, like the parent of 3 is 1, I'm sorry, the parent of 1 is 3 and its color is 1. That means it doesn't respect, right? So basically the parent and the color is given, okay? So what I am doing is I am storing the color of every node, and also I am making an adjacency list that for every node what are its children, right? So vector of int, and now I just taking the input for int I equal to 0, I less than I plus plus, int parent comma type, c in parent comma type. If type equal to 0, then good of I equals to true. So good of I true means that it respects its parents. Okay, so it is good. So I just stored this information, and if parent is not equal to -1, that means it is not the root. Like for the root it is -1 in the input, right? So if it is not the root, then I will push adjacent of parent -1 dot pushback I. Parent -1 because in the input it is 1 indexed, and I'm making it 0 indexed, right? So this is the input, and then what we do is we just iterate over all the nodes. Okay, like I just iterate over all the nodes for int I equal to 0, I less than I plus plus. First of all, if it is good, that means if it is 0 itself, then it cannot be deletable, right? Now I just iterate over all the childs. For auto x in the adjacent of I just iterate over all children. If good of x, that means if the child is 0, if the child is good, then flag equals to false. Like if any child is 0, then I will make this flag equal to false, right? And if flag, that means all children are 1, so I will mark it as deletable, like ans.pushback I plus 1. I plus 1 because 1 indexing. Okay, so this ans vector will contain all the vertices which are deletable, right? And then we'll just print all of them, right? And like if the ans is empty, like if the ans is not empty, then we'll print the ans vector, and if it is empty, then it will print -1. That's what they want from us. All right, so this is what you can do. That's how we can solve this problem. And the time complexity of this is just O of n, because we have this for loop. So like this for loop is O of n, right? And also, I mean, it's just input, right? And then this for loop is also O of n, because like for every vertex we are iterating, and for every vertex we are iterating over its children. So like this for loop will be O of degree of I, the degree of node I, right? So in total it will take the sum of degrees number of time, and sum of degrees is what? It is the number of edges. So in total this for loop will be O of n, because the number of edges is just n minus 1, right? So this was the time complexity. Time complexity is O of n, and space is O of n because we need to store this adjacency list. Adjacency list we need to store, so space is O of n, right? So yeah, I thought so I think this is what the solution is, and I hope you understood this, and thanks for watching.